Welcome to Calc 3. This is section 14.3, line integral over vector fields. So recall that the divergence of f is given by the del dot f, where del is the vector of partial derivatives, partial x, partial y, partial z. Del is an operator vector. The curl of f is given by del cross f, and the line integral over a curve C is parameterized by r of t on a surface S is given by the integral over C, f of s ds, is the integral from a to b of f, where you parameterize f by the curve r, dot the magnitude of the velocity vector r prime dt. And if, for a field f, if you have f is equal to some gradient of a surface function phi, then phi is called the potential function of f. So these are some key definitions we'll need today. So let's let f be a vector field. C is a smooth curve, and t is the unit tangent vector of r of t, where r of t parameterizes the curve C. So we say that the line integral along C over the vector field f is given by the integral over C of f capital F dot dr. Remember, the vector field is given by a capital letter, which is equal to, from the integral from a to b of capital F evaluated at r of t, dot the velocity vector r of t dt. Notice the similarities between the line integral over the surface, little f of r dot magnitude of r prime, and vector big F evaluated r dot the vector r of t. So here in the previous one, we had a scalar valued function, so we dotted it with a scalar. Here, big F will be a vector valued function, so we dot it with another vector in order to get a scalar on the inside of our integral. A scalar valued function, it could still be a function of t, but it is not a vector, it is a scalar valued function. So let's do an example here. So let's let capital F be the vector field x comma x plus y, and let C be the curve y equals x squared, starting at the point 0, 0 to the point 1, 1. And we want to find the integral of f dot dr. So when we look at this curve, the first thing we have to do is we have to parameterize our curve. So let's let x equal t. And so this means that y is equal to t squared. So our curve r of t is equal to the vector t comma t squared, from t equals, t is an element of 0 to 1. So r prime of t is equal to 1 comma 2t. So then we take this and we insert this into our vector field using our definition given above here. The vector from over C of f dot dr, we have by our definition is from 0 to 1 of the vector field evaluated at our r of t, dotted with our r prime dt. So this is our vector field 0 to 1. Our x component is given by t. Our y component is given by t plus t squared for our vector field, dotted with 1 plus 2t, and then dt. So from here, we evaluate the dot product, so we get t plus, excuse me, dropped, that should be a comma. So we get t plus 2t squared plus 2t cubed dt. And this is an easy integral to solve. So this becomes t squared over 2 plus 2/3 t cubed plus 2 over 4 t to the 4th, evaluated from 0 to 1, which gets us 1/2 plus 2/3 plus 2/4, which is equal to 1 plus 2/3 as our answer. So that would be the line integral over the vector field f, would be where this is our vector field and this is our curve. So this is our solution for this problem. So our vector field, if we have a conservative vector field, we have, if F is a vector field on an open connected domain, here connected means that if you have any particular point, you can get to any other point without, in your domain, so by any sort of curve, so by a curve rather, there's a path between any 2 points in your domain. This is what it means to be connected. So if F is a vector field on an open connected domain containing 2 points A and B, then if the line integral over that, along C over the vector field has the same value for all choices of paths from A to B. If this is true, then we say F is conservative and the line integral is path independent, and we write it as A to B of F dr, F dot dr. So if it doesn't matter what choice of path we take from our 2 points, we say the field is conservative and the integral is path independent. And this brings us to the key theorem for line integrals. This is the fundamental theorem of line integrals, or FTLI, the fundamental theorem of line integrals. So let's let F be a vector field with continuously connected components and with points A and B in our domain and a curve that goes between A and B. So we have 2 parts. If our vector field is connected, then we have a potential function, phi. And if we have a potential function, then our vector field is connected. So we have an if and only if statement for part 1. F is conservative, not connected. So F is conservative if and only if it has a vector field. F is conservative if and only if it has a potential function phi. If F is conservative, then we can essentially do the fundamental theorem of calculus using that potential function. So the fundamental theorem of calculus says take our potential function evaluated at the points B and A, where B and A are the start or finish and the start, respectively, of our curve. So if we have a conservative field, then this is equivalent to doing the FTC in the same way that we did in Calc 1. And this is pretty awesome. So an additional theorem that's helpful is that if we have a conservative field, then our curl is equal to 0 in 2 dimensions, or our curl is equal to the 0 vector in 3 dimensions. And if the curl is equal of our vector field is equal to 0, then we have a conservative field. So these 2 theorems, the fundamental theorem of line integrals and our connection between conservative field and curl, will help simplify a lot of our problems. So let's look at an example here. So let's find the potential function if it exists of this vector field 2x minus 2x comma negative 2y comma 2x times y. So the first way to check is to use the fundamental theorem of line integrals in conjunction with the theorem that if F is conservative, we have the curl is 0. So let's check the curl to see if F is conservative, because if F is conservative, by part 1, we have a potential function and then we can find it. So this is a 3-dimensional function, so we can check the curl of F using the cross product. So we have our I, Rj, and Rk. So partial partial x, partial partial y, partial partial z. And we have 2x, negative 2y, 2xy. And so we check this curl. So we do partial with respect to y. We get in our first point 2x minus 0. And then our partial with respect to x. So in our j component, we get negative 2y plus 0. And our partial with respect to our k component, we get 0 minus 0. So we get 2x, 2y, comma 0. This is not equal to the 0 vector for all x, y, z. So this means that our curl of our vector field is not equal to the 0 vector. So this means our field is not conservative. So since our field is not conservative, by our fundamental theorem of calculus, or fundamental theorem of line integrals, we have no potential function. So we don't have to go through the process of finding a potential function because we don't have one to begin with. So this is a really helpful property. So the next example here, let's look at a vector field F where we have 2x plus y, 2y plus x, and we want to find the line integral over the vector field or the curve C, where C is given by r equals t squared minus t cubed minus t from t equals 0 to 1, and also separately from t equals 0 to 3. So let's look at this two different ways. So let's look at this option 1. Let's do it using the definition of our line integral. So we use this definition here from A to B of our vector field evaluated at r dot r prime dt. So this gives us from 0 to 1 of our vector field. So we substitute in our vector r into our vector field. So we get 2 times t squared minus t plus t cubed minus t, comma, 2t cubed minus t plus t squared minus t, dotted with the derivative of r, which is 2t minus 1, comma, 3t squared minus 1 dt. And we can simplify this out, so we get the integral from 0 to 1 of t cubed plus 2t squared minus 3t, comma, 2t cubed plus t squared minus 3t, dotted with 2t minus 1, 3t squared minus 1 dt. And this is just a huge polynomial. So when we dot these components, we'll get the line integral from 0 to 1 of some polynomial in t with respect to dt. And this is easy to solve, but it's tedious. So it's just some algebra, easy but tedious, and it's not terribly interesting. And so for this particular problem, it's not too hard, but let's look at a different option. So let's find a potential function phi, if it exists. Because if it exists, then we can use the fundamental theorem of line integrals. So if the phi exists, then we can use the fundamental theorem of line integrals. So let's first check that the potential function exists. So f is equal to the vector field 2x plus y, comma 2y plus x. And the curl of f, our shorthand, in 2 dimensions is nx minus my. So n sub x is equal to 1, m sub y is equal to 1, so we get 0. So this means that phi exists. This is a nice check to make sure that we have a potential function before we try to find it. So phi sub x is equal to our first component, 2x plus y. Phi sub y has to be equal to our second component, 2y sub x. So integrating both components, we get phi is equal to the integral of 2x plus y dx, as well as equal to the integral of 2y plus x dy. Those have to simultaneously be true. So this gives us x squared plus xy plus some function of y, y squared plus xy plus some function of x. And as we've done this problem before, we see that phi is equal to x squared plus xy plus y squared. So our potential function here exists, plus some integration constant. We can tap on our plus c here. So we have phi existing. So since phi exists, that means our vector field is conservative. So f is conservative. which means that the line integral over c of f dot dr is equal to phi of b minus phi of a. So we just need to find what b and a are. And here, a is equal to the curve evaluated at t equals 0, which is equal to t squared minus t, comma, t cubed minus t, evaluated at t equals 0, which is equal to 0, 0. And b is equal to r evaluated at t equals 1, which is equal to 1 squared minus 1, comma, 1 cubed minus 1, which is also equal to 0, comma, 0. So since we start and stop at the same place, phi of, by our definition of integrals, we have, just as in Calc 1, start and stop at the same place, we have gone nowhere. So that means that our integral equals 0. And we can check this because if we said our phi of x comma y is equal to x squared plus xy plus y squared plus c, phi of a, or phi of b, is equal to 0 plus 0 times 0 plus 0 plus c. This is our phi of a minus our phi, or sorry, phi of b minus our phi of a, which happens to be the same thing. We get equal to 0. Our second component here, if we're evaluating from t on the interval 0 to 3, then our b value here is equal to the point 6 comma 24. 624. So that means that phi of b is equal to 6 squared plus 6 times 24 plus 24 squared plus c. So phi of b minus phi of a is equal to 756. And that is the answer for that integral. So as always, if you have questions, please let me know.